Hi friends, now we are going to learn another algorithms under greedy method called Prim's algorithms. Very important concept, and based on this Prim's algorithm we are going to find out minimal spanning tree. This is called minimal spanning trees. Now before that we have to learn, right, what is spanning trees, right? Then we will discuss what is a minimum cost spanning tree or minimal cost spanning trees. So this term is very famous, minimal spanning trees, okay, or this is also called in short form MST, minimal spanning, right, tree. Okay, so what is this Prim's algorithm? Prim's algorithm is to find minimal spanning trees or minimal cost matrix based on the given problem scenarios, right? We will not able to understand now what we are talking about MST, minimal spanning trees. First we are going to learn what is MST and how you are going to apply this Prim's algorithm by using greedy method to find minimal spanning trees. Look, what is a minimal spanning tree? It is a subgraph of n, subgraph of undirected weighted graph, right? Now what is the undirected weighted graph? I am going to give you the example such that it is a trees. All of you have studied in the previous semester what is trees, what is banded trees and all. So remember that when you are talking about the trees, tree is looks like this, right? Do you have any cycle in this? No. So if you are talking about the number of vertex, right? So how many number of vertex you have? I am just making round number of vertex. 1, 2, 3, 4, 5, 6, 7. So n is equal to 7. But how many number of edges you have? 1, 2, 3, 4, 5, 6. So number of edges is 6. Can be written as n minus 1. 7 minus 1, 6. Remember, then we can say that minimal, when you are saying minimum spanning trees or spanning trees is a trees, right? It is a trees, or you can say it is a cyclic graph, a cyclic graph. So we can see that in this we don't have any cyclic path. Hence it is acyclic, and whenever acyclic is there, number of edges will be one less than the number of vertex. When it is a cyclic path and we have more number of edges, then this property will not valid. Number of edges must be one lesser than the number of vertex. That is a property of trees. So it covers all the vertices of V, contains V minus 1 edge. Number of edges will be one less than the number of vertex. The total cost associated with a tree's edge is called minimum among all possible spanning trees. Now, if I am telling you that this is A, B, C, D, and we are connecting like this, which kind of graph it is? It is undirected graph. Okay, this graph is undirected graph because we don't have any weight on it and we don't have directions. Now if I am writing here 5, 10, 15, 20, 7. Now weight is there on edge, weight or cost on their edge. Then this graph is called weighted undirected graph or undirected weighted graph. When there is no weight but there is no direction on edge, then it is called undirected weighted graph. So point to be noted that what is the difference between undirected graph is there is no directions on their edge. Undirected weighted graph, when there is a weight on their edge but there is no direction on their edge. Okay. So this kind of graph you are going to use for our purpose. Let us example. Which kind of graph it is? Do you have any direction on their edge? No, there is no directions. Hence it is undirected graph. Do you have weight on their edge? Yes. Hence it is undirected weighted graph. No. Remember that based on one graph, we can have many spanning trees. Now, what is a spanning trees? A spanning tree is where all the vertices are present. A spanning tree is what? All vertex or vertices are present but not all edges, right? Is called a spanning trees. Is called a spanning graph. A spanning graph. Okay, when all the vertices are present but not all the edges is called a spanning graph. But what is spanning trees? How it is different? A spanning trees, all vertices are present and number of edges is equal to number of vertex minus 1. Number of edges is equal to number of vertex minus 1. So look at this example 1, 2, 3, 4, 5. There are 5 vertex. So all 5 vertex should be there, right? Now when you are talking about minimal weight, say as for example from here we have A to C is 5, A to B is 9, A to D is 2. So can we go like this? Yes. Now you are at a D, D to B is 6, D to C is 4, D to E is 4. So which one will come first? Maybe this will come first. So we can go like this. From here even this is 4, so we can go like this. Now at this point here we have, see from B we have 9, from B to D we have 6, B to E you have 5. So maybe this is lesser weight, we are going to select like this. So how many vertex we have selected? We have selected A, D, B, E, C. So all 5 vertex are there. How many edges we have selected? 1, 2, 3, 4. 4. It is 5 minus 1. So basically this cost on their edge, if you are selecting such a way that cost of the trees, which kind of graph you can see that? It is a trees, right? It is not a cyclic, it is free from cycle. It is free from cycle. So if it is free from cycle, then it is a spanning graph, and number of edges is 1 less than the number of vertices, hence it is called a spanning trees. And which kind of a spanning trees? It is called minimum cost spanning trees. We can have multiple solutions. Say here person can go like this. A to B is 9, B to D is 6, right? Then say here we have C to A to C is 5, right? Then we cannot make it cycle, it will be getting cyclic path, and we can make here like this, C to E is 5, right? So if we'll add this weight, we are having 1, 2, 3, 4, 5, but if we'll add this cost, 5 plus 5, 10, 10 plus 6, 16 plus 9, 25. Weight of that particular spanning trees. What is the weight of here spanning trees? 2 plus 4, 6 plus 4, 10 plus 5, 15. Here total cost is 15. In this case cost is 25. Remember that this is the minimum cost. This is the minimum cost. Hence it is called minimum cost spanning trees, or you can say minimal cost spanning tree. Minimal cost spanning tree. Now let us see that what is Prim's example, right? And we must understand that graph in this particular case, Prim's algorithm, Kruskal algorithm, we are giving graph as an input. We are giving graph as an input to the program. And remember that we cannot give graph as an input. Hence, we are changing this graph form to adjacency matrix. Right? So there is two ways converting graph into that, adjacency matrix as well as adjacency linked list to give the input to the program. So here we are talking about adjacency matrix. And which kind of graph it is? It is weighted connected graph. So let us see that here we have examples, say A, B, C, D, E. This kind of graph we have. Say it is 2 unit, 3 unit, 4 unit, 7 unit, 4 unit, 5 unit, 6 unit. Right? If we give, this is which kind of graph? Undirected graph, undirected weighted graph. This we cannot give input to the program. Then how we will give? We are going to construct adjacency matrix. As we have discussed in BFS and DFS, A, B, C, D, E. A, B, C, D, E. If there is no direct path, we are considering as a infinity. A to A, do you have A to A path? Just keeping 0. A to B, 2. A to C, no direct path, hence we are writing infinity. But in a program, at the place of infinity, we are going to write bigger values. At the place of infinity, just we are writing some bigger values comparatively bigger than this. So these all are the single digit values. We are writing 999, it is very, very large values. Hence, because infinity you don't have on our keyboard, hence we can represent in a program with some larger values. So you are writing infinity. A to D is infinity. A to E is 7. B to A, same undirected means A to B and B to A is same. So it is 2. B to B 0. B to C 3. B to D again infinity. B to E is 4. C to A infinity. C to B 3. C to C diagonal element 0. C to D is 6. C to E is 5. D to A is infinity. D to B is infinity. D to C is 6. D to D 0. D to E 4. E to all the vertex. E to A 7. E to B 4. E to C 5. E to D 4 and this. So what is this? This is called adjacency matrix. We require this when you are talking about the program. Otherwise, we are not able to perform the task. Clear? Now, how are you going to apply this Prim's algorithm in order to find out the minimal cost spanning trees? So let us see that. Again, we will rewrite this. Again, we will rewrite this example and try to solve it. So here we have A, B, C, D, E, 2, 3, 7, 4, let me see, 4, 4, 5, 6, 4, 5, 6. Okay. So I have taken the same example. Now, in order to solve these Prim's algorithms, so let us have, we are selecting that vertex, right? We have remaining vertex, remaining vertices, and we have illustrations, or we can say that tracing of those points. So in this particular case, first we need to identify the source vertex. Source a place from where you are going to start the journey. So say we are starting the journey from A by default. Otherwise you can select any vertex as a source vertex. So if you are selecting source vertex as A, then we are going to start from A. We are going to start from A. Do you have direct path from A to B vertex? Yes. So how are you going to write? There is a direct path from A to B. You are writing B, A to B, not B to A to B. So B is the destination. So B first, then A comma. What is the distance? It is a 2. Similarly, do you have distance from A to other vertex, A to C? No, we don't have it. So just we write it C comma, you can say infinity. Then D, it is again infinity. E, we have a path A to 7. A to 7. So from A to B, A to C, A to D and A to E we have written it. Out of this, what is the minimum distance, friend? 2, infinity, infinity, 7. So out of 2, infinity, infinity, 7, 2 is minimum. So we are selecting B vertex as a new source vertex. So this is been already traced. So how are you going to write it? You are going to write it again A to B, B to C, C to D and D to E. And what I am trying to say that this we have already selected, right? And what is path? Path is weight is 2. Similarly, remaining all age we can write it 3, 4, 5, 6, 4, 7. Now we are at B. From B we are going to write all the vertex. So since B to A is already done, we are not going to redo it. Do you have any path from B to C? Yes, we are going to write C, B comma. What is the distance? It is 3. From B, do you have path from D? No. So we will writing D comma infinity still. No. Do you have path from B to E? Yes. Look, B to A to E was 7. B to E is 4. Right? It is 4. It is 4. So 4 is lesser or 7 is lesser? 4 is lesser. So we will write it E, B comma 4. So we will update the weight also if there is lesser weight in the future. So our tendency is to find out the minimum cost. Hence, compared to 7, A to E, B to E is smaller, so B to E we have selected. Now we have a 3, we have infinity, we have 4. Which is lesser? Of course, 3 is lesser. So we are going to select C, B comma 3. If we are selecting this, again we are going to rewrite A, B. We already selected this path. Now we are selecting this as well, and here we have a C. Rest of all the vertex we have as it is, right? So this is 2, this is 3, and this is 4, 5, 6, 4, 7. This is the present scenarios, and we have selected C. Now we are at C. Can we see that traverse C to D? Yes, there is a path from C to D. So we are writing here D, C comma. What is the path? C to D is 6. We will be writing 6 comma. Do you have path from C to E? Yes, we have it, but C to E is 5, where B to E was 4, 5, 4. Which is lesser? 4 is lesser. If lesser value is there, we are not going to update it. Only we are going to update with the new values which is lesser than previous iterations. So always our tendency is to find out lesser values, minimum values. Hence, we are not going to update these values. We can check here A to E was 7, B to E got 4, so we have updated it. But in this case, we are not going to update. We leave as it is because C to E is 5. In this case, now here you have 6, here you have 4. Which is lesser? 4 is lesser. You take it out. And which vertex set you are going to take? E, B comma 4. So similarly, we are selecting this particular edges. Right. So E, B comma 4, we have selected this, right? So we can rewrite it A, B, C, D, E. So this one you have selected in previous iterations, this one you have selected, now we are selecting this as well, right? So this is our present scenarios. Now we are at E. Do you have path from E to other vertex? Do you have path from E to other vertex? Yes. E to D. E to D we have a 4. So D is only pending. C to D was 6. C to D was 6. But E to D is 4. So 4 is lesser. So we are going to write it here. D E comma 4. C to D was 6. E to D is 4. So we are going to update the values by lesser values called 4. Hence we are going to select this D E comma 4. So this edge is selected. Hence in next iterations we have selected this particular edge as well. Okay, and what is the value? It is a 4. So look what a graph you got it. Earlier it was cyclic path, many cycle, 1, 2, 3. So many cycle was there. Number of vertex, how many number of vertex was we are having it here? 5. So actually number of edges must be 5 minus 1 is equal to 4. How many edges we are having it? 1, 2, 3, 4. So this is our spanning trees. And which kind of spanning trees? Because you have gone for the minimum values, smaller values, hence this is called minimal spanning trees. This is called minimal spanning trees. Right? So our answer is A to B, B to C, B to E and D to E or E to D is a final answer for minimal spanning trees. So how are you going to write it? So outcome of this is, output of given example is A to B, B to C, B to E and E to D. Is it a trees? Yes. Minimal spanning trees. Okay. What is cost of this tree? Total cost is 2 plus 3 plus 4 plus 4. Right. So hence it is 13. Right. What else? If you are going to print all the path, so we are saying that there is a path from A to B, B to C, B to E and D to E or E to D. So these all are the solutions for given example. A to B we have a 2, B to C we have a 3, B to E we have a 4 and D to E we have a 4. Right, again we will get 13. So these are solutions to Prim's algorithms. So let us see next what is that and how you are going to correlate with the program. Look, Prim's algorithms, we have a weighted connected graph, right, G, V, comma E, where V is a set of vertices and E is a set of edges. Right, fine. And what is our output? Output should be set of edges composing a minimum spanning trees. So VT initially we have is V0, ET we don't have any edges. Why V0? We are just selecting one source vertex to start. We can select any vertex as a source vertex. Now 1 to V minus 1. Remember that when you are saying the V minus 1, number of vertex minus 1 is corresponding to number of edges. Number of edges. That many number of iterations to be performed. If you see in this particular case, how many iterations we have done it? 1 selection, 2 selection, 3 selections, 4 selections. And we have 4 edges only in your answer. Hence, this will give you the number of iterations to perform. Find the minimum weight edge E, V, comma U. Remember that V, comma U is from V source to destinations V, comma U. Among all the edges V, comma U such that V is in VT, V is a part of set of vertices and U is in V minus U, means a vertex is not visited. V minus VT is set of vertices not visited or not considered. Okay, not considered for that trims. So VT we are going to write VT union U. U is a new destinations. We are just finding the union or you are adding that vertex into that set of vertices. Similarly, edges, you are going to add it, new edges as a set of edges, return et. Same things we did it over here is, initially we don't have any edge, first we have added this edge, right, and this vertex, this was the source, then you have added b also, then you have added c also, e, then d, and slowly we have added these one by one all the edges as well. So we are just finding that particular vertex which is having lesser cost from that source, and that particular edges also you are adding in the edge matrix. So this is the algorithms. Then summary, Prim's algorithm used to find the minimal spanning trees using greedy technique or greedy method you can say, and time complexity is E log V, where E is a number of edges and V is a number of vertices. Okay, E log V base 2, right? This is the time complexity for the Prim's algorithm, because for each and every point we are traversing all the remaining vertices. So number of edges is from for loop. Yeah, how many number of times? 1 to v minus 1 means total number of edges. And what are we going to do it, friend? We are going to traverse this again and again, and finding that particular values. Hence, time complexity will be, as we have discussed in the previous concept, in divide and conquer and all, how to find the time complexity, right? So in similar way, time complexity for that time, Prim's algorithm is E log V. So this is a summary of Prim's algorithm. Thank you very much. We'll meet you in the next class.